Cool beans. And if you can do these, then you should be pretty good on these type of problems for your exams. So I hope I go through it very well and explain it well that you understand. Okay, so consider the reaction below, and this is our reaction of hydrogen. Um, uh, Fluoric acid is what it is, plus water, kind of breaking up, dissociating, and we have a delta G changing Gibbs free energy. This is of the reaction. It doesn't say that, but it's of the reaction. It's negative 18.2 kilojoules per mole. And we want to find, so this is the standard Gibbs free energy. Okay, this is the standard Gibbs free energy under 1 bar. But here, we want to know what the change in Gibbs free energy is if we're given certain concentrations. So these are like initial concentrations. And this actually, yeah, initial concentrations here. So I'm going to move this down because we'll tackle the next one in a minute. So to find out what the change in Gibbs free energy is for some random kind of initial concentrations, we need to use this equation. The delta G equals delta G naught plus RT ln Q. And some schools may put this as K trial or some profs, but Q is the reaction quotient, which is like the equilibrium constant, except it's not at equilibrium, that's at any time. So that's cool. So we'll plug this in. So this is negative 18, we'll do it right away. Well, negative 18.2. This is in kilojoules per mole, but R is in joules, right? R is in joules. So I'm going to convert this to joules first, times 3 joules per mole, plus, now R is 8.314 joules per mole Kelvin. And the temperature, so they did this again. So if they don't give you a temperature, you have to assume it's 25 degrees Celsius. It's 298 Kelvin. It doesn't have to be. It could be a different temperature, and they really should specify that. But again, this is the exam problem where we're given, so we got to kind of work with it. Now, Q is products over reactants. So Q is products over reactants. So it'd be the concentrations of the products divided by the concentrations of the reactants. So concentration of F minus times the concentration of H3O plus over the concentration of HF. And then water is a pure liquid, so we don't include it, pure liquids and solids, into the equation here. If there were numbers here, if there was like a 2 here, then this would be squared. We just take this stoichiometric coefficient. It becomes a power in here. Okay, so we'll plug this in. Actually, I'm going to do this all in one fell swoop. I'll make this one big bracket, and we're given concentration. So these top ones are 0.1 molar, 0.10. And I'm not going to include units. This is actually unitless. We're actually taking the concentration, dividing it by a standard concentration of 1 molar, assuming these are perfect solutions. But if you're in general chemistry, you probably don't have to worry about activities and whatnot. So you just kind of plug in the numbers. And as long as these cancel, the units are the same. I mean, as long as the units are the same, then Q will be unitless overall. Okay, so this is 0.0001 10 to the negative 4, really? Okay, and then we'll close our brackets, should probably make it square brackets, but that's okay. Okay, so negative 18.2 times 10 to the power of 3 plus 8.314 times 298 times, now we need ln, where's our ln? There's our ln, and 0.1 times 0.1 divided by 0.0001. Does that look good? I think we're good. Okay, what is it? All right, so a negative number. So negative 6790, negative 6790, and this has to be in joules per mole. Kelvins cancel out. This is unitless, so this is in joules per mole. Joules per mole. So delta G is equal to this number, joules per mole. We'll put in kilojoules. We'll multiply, divide it by 1,000. So 6.79 kilojoules per mole. And is that what we want? Or are we done? We're done. Okay, so that's it. So the way it is right now, this is negative. So under these conditions, This is spontaneous to the right with these concentrations right here based on this. Yeah, so we'll produce more of this, which makes a lot. Does that make sense? Well, this is, we don't have a high concentration of HF. We have a high concentration of these things. But yeah, if we look at the number, this is quite negative, so we're spontaneous to the right based on these concentrations. Okay. All right, so moving along, we have another one here. We want to know, okay, so this is the same equation or same reaction. I'm going to move this up a bit. But we now have different concentrations with the same equation. So before you skip to the next one, I think it's instructive to look at this. But I'll just, rather than kind of talk through everything, we'll just kind of get to the end result. The change in Gibbs free energy equals the standard change in Gibbs free energy plus RT ln Q. Now, this is the same because the reaction doesn't change. It is negative 18.2 times 10 to the 3. Negative 18.2 times 10 to the 3 joules per mole. R is still 8.314 joules per mole Kelvin. Temperature is still 298, we have to assume. Now the Q is going to be products over reactants. So it's these two. Oh, these are almost the same numbers, but they're slightly different. Ln of 0.10 times 0.10 divided by 1, 2, 3, 4. There's 4 zeros. How many were last time? 3. Okay, 0.1, 2, 3, 4, 1. Okay, so we'll plug that in. Oh, I wonder if I can just redo this and add another 0. Can I do this? Another 0. Everything else is the same. Okay, it's still negative. So negative 1085.5, negative 1085.5 joules per mole. And in terms of kilojoules, 1, 2, and 3, that's negative 1.08 kilojoules per mole by dividing it by 1,000. It's barely still spontaneous to the right. If this was a little bit smaller, say another factor of 10, then would very likely be positive, so we'd be spontaneous to the left. Okay, I hope that was very thorough. Good luck on your midterms. Good luck on your final exams and quizzes. Thanks for watching. I hope it helped. And I've got many videos on thermodynamics and other aspects of chemistry, so check them out. Good luck.